Hey guys, so I'm here today to give you the 12th lecture. This is going to be on Newton's third law and some practice problems as well. Basically, we're gonna hit some of those practice problems we did in the previous lecture and just go through the solutions. There was also a mistake on at least one of them where I didn't read the problem closely enough. So maybe if you did and you caught that, that's great. But in any event, we're gonna get going. Okay, so share my notes. And there we go. And so what we're going to talk about, first of all, is Newton's third law. Now, Newton's third law it's something you've probably heard before, and I'll start you off with the colloquial definition. Not definition, just a colloquial statement of the law. It is for every action, there is an equal and opposite reaction. Now, this has cropped up all over the place in television and movies. It's a great line if you're telling a revenge story or something like that. But in physics, we mean something much more specific. And basically, what I want to do is I want to tell you what this means in physics terms. It means for any force, and I'm going to call this F sub AB. And what I mean by this, I'll make it a vector. What I mean this is a force F on object, well, let's say object A, on object A from object B. Now, it is important that in some sense, forces can always be traced to object. Forces, you can't have a force without some object exerting a force. So this is something you can always identify. And if you're looking for third law pairs, then it really does start to help. It helps to start with this to say, okay, which object is this force acting on, and which object is it coming from? Okay. Now, so for any force like this, what this is saying is there also exists F sub BA. And what this is a force. I guess I should just say, I don't want to confuse me. This is a force on object B from object B from object A, such that, and this is the key, that the force from A, or force on A from B, is opposite and equal to the force on B from A. Okay. So this is basically what is being said here. Now, this can come up, and it can be kind of confusing how this works. So I want to just give you a couple of notes. There are two big points about the third law. Now, um, actually, before I do this, I'm gonna put this in bold. We call FAB and, or sorry, yeah, that's exactly right. And FBA, third law pairs. Okay. So these are third law pair forces. Now, there are a couple of things to note about them. So notes about third law pairs. And one of the big things about it is, and the first one is that third law pairs act on different objects. Okay. They are not acting on the same object. They are acting on different objects. So a third law pair, two pair, or a pair of third law forces will never both impact the same object, unless that I mean, unless you're kind of viewing a system as a single object, in which case we don't really pay attention to those. But the idea is that you're not, for this reason, the reason I'm telling you this is that third law pairs are never included in the same free body diagram. Third law pairs are never included in the same free body diagram. Okay. So that is the key with third law pairs. This is why, you could say something like a common question that comes up where people they don't really understand what's going on. They're like, well, if there's always an equal and opposite reactive force, how is it that forces can actually cause anything to happen? And the key is that, sure, the idea is that, okay, if I push a ball across a room, the idea is that, yeah, the ball is pushing back on me, but though it's not like though both of those third law pairs are acting on the ball, okay? The only one that's acting on the ball is my push from the ball. The push from the ball is acting on me, and I've got other forces that basically make that push from the ball functionally, not really affect me much. Whereas my push on the ball does affect the ball quite a bit. So because they're not on the same object, they don't really ever, third law pairs do not affect the motion of a single object. That's important to remember. Okay. Now, another thing to know is that they were always the same type of force. Okay. So third law pairs are always, always, always the same type of force. Thus, if one force is a normal force, its third law pair will also be a normal force. If a force is an applied force, applied force is a broad category, but whatever that happens to be, the third law pair force is also an applied force. If a force is a gravitational force, the third law pair is also a gravitational force. Okay, so I want you to keep that in mind as I show a quick example of this. So just an example of a book on a table. And I'll draw the diagram. Now, what I'd suggest is go ahead and pause. See if you can draw the free body diagram of the book and see if you can identify the third law pairs of the forces that you've drawn. So go ahead and pause that. But if you do that, what you should get is you should get a free body diagram that looks basically like this. So you've got F sub G, and that's just equal to mg. And then you would have your normal force, and we could state this, tell you what, I'll do mass of the book times G, and then normal on the book from the table. That's the way I'll put that. Okay. Now we know that because this book is not accelerating, then those two forces have to be equal. Now the mistake people will make is they will say, okay, well, this must mean that those are third law pairs. That's not true. Okay. The normal and the force of gravity are not third law pairs. You got to be really clear on that. All right. We'll talk about what the third law pairs are, but judging by we'll do this in red. Judging by what I said in the second point there, third law pairs. Start with the force of gravity. The force, and I'll just do on the book of gravity. Okay, what is the third law pair of that one? Well, the main thing that you can do is that you can say, basically, it's say force of gravity, and I'll just say on book to be clear about that. Now, when we just write the force of gravity, it's not immediately clear what that's from, but you probably know that gravity is exerted by the Earth. Okay, so the third law pair then is also a gravitational force, but it's on the Earth from the book. Now, the idea here, if this book is, say, 1 kilogram, then the gravitational force on the book will be 10 newtons. Okay, not very much, but enough to accelerate it. at the acceleration due to gravity. Question then some people have, well, if the same force is on the Earth, why doesn't it accelerate upward? Well, here's the thing. The same force does not mean the same acceleration. A 10 Newton force on the Earth is basically nothing. I think I just checked this. I believe it's on the order of 10 to the 25 kilograms. Okay. 10 newtons on 10 to the 25 kilograms being the mass of the Earth, that has no measurable effect. You could not measure the acceleration even if you wanted to. And then you'd also have to take into account all the other gravitational forces from other objects. The point is that this force, it has negligible effect. But the third law pair also needs to be a the third law pair needs to be a gravitational force. Now, for the normal of the book on the table, when you have something like this, if you write as two subscripts, the one that it's on, sorry, normal on the book from the table, the one that it's on first, the one that it's from second, it's actually quite easy to just say, okay, it's the same type of force, in this case, a normal force, and it's on the table from the book. Okay. And the idea here is that the book is going to exert a normal force downward on the table. Okay. And that is in response to the upward normal force that the book is exerting on the table. Now, if this doesn't really make sense, I'm gonna give you a slightly different example. The normal, like if you think about like a bowling ball, like we could have a bowling ball in a similar situation, make it 10 kilograms. That'd be a heavy bowling ball, but whatever. 10 kilogram bowling ball. We set it on the table. It would more or less set like this, and the normal would be equal and opposite to gravity. Now, if I took that same bowling ball, not changing the force of gravity at all, remember, same force of gravity, and I drop it from 100 meters up, that would shatter the table. Okay. And the reason is that basically what happens is the normal force doesn't not just need to support gravity, it also needs to decelerate the ball. So it needs to be a whole heck of a lot higher than the force of gravity. And because the normal force from the table needs to be a whole heck of a lot higher, the normal force on the table from the ball has to be a whole heck of a lot higher. And that force is enough to break the table. Okay. So that is kind of what's going on with third law pairs. All right. So it's worth keeping in mind. Another question that often comes up in the context of third law that I want to give you. Question. All right. A fly hits the windshield of a truck. Which force is greater? The force on the fly? The force on the truck? Or neither? So pause this and think about not just do you know the answer, but why this is the case. Okay. So the correct answer is that neither. Neither is greater. They are equal and opposite because the force from the windshield on the fly is the third law pair from the force of the fly on the windshield. And people look at this, they're like, there's no way those are the same force. They had a wildly different effect. The truck, nothing happened to it, and the fly got liquefied. Okay. Well, here's the thing. Just because the force is the same, and this is the key to remember, just because the force, I'll even write this down. Just because the force is the same, the force is the same, does not mean that the effect is the same. Okay? Because the effect fundamentally is related to the acceleration of the object. So the observed effect of this force on that fly, basically, if we were going to talk about that in physics terms, the effect is acceleration of the object. Now, you know from Newton's second law that there's something else besides force that affects the acceleration of the object, and that is mass. And that is the thing that is happening here. This force is actually quite a small force. The force on the fly and the force on the windshield are actually quite small forces. They're not big. Now, because the fly is such little mass, even that small force can have a tremendous effect. Basically, again, the fly gets liquefied. But that small force has a negligible effect on the truck. Okay, that's the important thing to remember. All right, it might slow the speed down ever so slightly if if the person wasn't putting on the accelerator or something like that. But that is the idea. Okay, and again, acceleration also depends on mass. So this is the other thing to keep in mind, is that third law pairs, even though they may be the same force, that does not guarantee that they will produce the same effect, because a lot of times the objects exerting them have huge differences in mass. Okay, so the huge differences in mass can mean, okay, even given the same force, you might have a wildly different effect on the object. Okay, so that's the key thing to keep in mind. All right. Okay. All right. I think I wanted to do one more quick example. Um, and this is if we have just we'll call this frictionless ground. Um, and we have M1 and then a bigger box, M2 right here. And we do some applied force to M1 and M2. Now, you probably know what's going to happen is that basically these two boxes are going to move as a single object. And you might just say, okay, I'm going to use a mass of M1 plus M2. Now, that is, creating a system of M1 and M2. And in this case, what you do is you would say the mass of the system is equal to M1 plus M2. And then you can basically treat M1 and M2 like it's a single object. Now, if two objects are stuck together like they are in this case, then this is particularly easy to do. It can be done if the two objects are not stuck together, but that's something we'll get into a bit more when we cover momentum. And then all you would do here is you would say, okay, I've got the force of gravity, which we now know is mass 1 plus mass 2 times g. And then we've got the normal on the system, and those two are equal to one another. And we have FA to the right. But so we know from this that basically M1 and M2 are going to be accelerating to the right. So, we have the acceleration of the system is, we'll just, I don't want to do numbers right now, but we'll just say it's to the right. Now, the idea here is that what we should be able to set up is free body diagrams of both M1 and M2 and still get the system accelerating to the right, okay? So what I would ask you to do now is see if you can come up with the forces that are on M1 and M2. Pause this, see if you can do it. And such that you still get an acceleration to the right. And I'll give you a hint that a lot of people will miss. FA, it's only touching M1. It's not touching M2. And whether that's a hand, and you can imagine if it's a hand and you push on M1, well, you push on the smaller box. Well, if it's up against that larger box, it will still move the larger box, even though you're not directly pushing on the larger box. So the question is, what force is pushing on the larger box? Okay, so I'd pause that, think about it if you can get it, but here's the solution. So we have FG1, that's equal to M1 G1. We have normal, and I'll just call this 1, and then I'll do a U for up, and you'll see why I'm going to do this. Those two are going to be equal. I'll double mark that one because I don't want to imply that they're actually equal to to these marks up here in the first free body diagram. And then what you have is you have an applied force, I'll make that a little larger, an applied force to the right. We don't know what that is. But here's the thing, is that you can imagine that if M1 and M2 are initially slightly separated, well, you start pushing on M1, it will close that distance, and then it will make contact with M2, and it can't go through M2, okay? It can't go through M2. So the force that prevents it from accelerating through M2 is a normal force. And this would be normal on 1 from 2. Okay, so in this case, there are two normals because there are two surfaces that M1 is contacting. That is allowed. All right, and that is what this one would like. Now we would say that, okay, we must know that FA is greater than normal from 1 on 2, because then you still have an acceleration to the right. Okay, so as long as that's true, we're good to go. All right. Well, from there, what we can do is we can say, okay, let's so this next one, this would be FG2, and that's equal to M2G, which is, we don't know what that is, but it's different than the other ones. And then we have a normal on box 2 in the upward direction, and those two are equal. Again, we don't know that they're not equal. We don't know that they're equal to these ones, and they're definitely not equal to the ones from the first diagram. Now the question is, well, M2 we need to have an acceleration to the right here. Now the problem is the applied force isn't going to the right, or it is going to the right, but it's not touching M2. So what force is? Well, the answer is that the third law pair, N2-1. So N1-2 and N2-1 are third law pairs. Okay, and so it's the normal on 2 from 1 that accelerates 2. So that automatically makes it an acceleration to the right, because there's nothing on the left. We don't have any friction here. And the last thing we can do is we can put these equivalence lines. N1-2 is equivalent to N2-1, at least in length. They are in opposite directions, but they are equivalent in length. Okay, and now this is why we have an acceleration to the right, no matter which free body diagram we use. If we look at the system, it's accelerating to the right. If we look at M1, it's accelerating to the right. If we look at M2, it's accelerating to the right. Okay, this is where if you were asked to analyze the forces on one of the boxes independently, this is where you'd need to imagine third law. Now note, we didn't include the third law pairs in the free body diagram. That they're in free body diagrams next to each other, but these are fundamentally different free body diagrams. They're acting on different objects. Okay, so that's the thing to keep in mind there. All right. Next thing I wanted to do was go through some of the problems, and here is one this is the one that I believe I did incorrectly the other day. So we'll do this one again. All right. So suppose two children push horizontally, but in exactly opposite directions on a third child in the wagon. First child. So we said before we said our system was the wagon plus child, basically. Child 3. And then we did our free body diagram. And first child, we call this F1. This was equal to 75 newtons. We also had the F sub G, which is M. That's the M that we were given, times G, and then the normal force. We can just do, since we know 23 is the mass, we can do 23 times 10, which is 230. And then the normal force is also equal to 230 newtons. So that's fine. Now the thing the other force, the force from child 2, is in the other direction. This was F2 is equal to 90. Now the thing I forgot last time was the friction force. It says friction force is 12, but we need to decide which direction it's in. So think about which direction you think it's in and just answer that. But it's going to be to the right. So friction would be equal to 12. And I'm drawing it above so I'm not crossing through my labels. And the reason it's to the right is that basically what friction does, like a good rule of thumb for figuring out what friction is going to do is it's going to oppose the direction the net force would be without it. Okay, so that's what happens here. And then when we do our F net, we really only need to do it in the X direction. We get, so to the right, we would have F1. Friction is also positive. And then minus F2, that's to the left. So we have 75 plus 12 plus, minus 90, because that's to the left. And when you add all those up, that will give you negative 3 newtons. Basically, what this means is 3 newtons left. That's what that negative means. And then from there, you can get an acceleration. So so for part C, it would be F net equals MA. So 3, we could say negative 3 equals 23 times A. A is going to be negative 3 over 23 meters per second squared. Again, another way of saying that, it's just 3 over 23 meters per second squared left. Now, because this problem doesn't give you, which direction should be positive or negative, I would suggest that if they are saying calculate the acceleration, but they don't indicate which direction is positive or negative. When they do something like that, just make it positive. This thing is accelerating in one direction. We could just as easily have let left be positive, or we could have just as easily put child 2 on the right and child 1 on the left. There's no directional specification of this problem. So that's the way that one would work. Now for D, if F were equal to 15, well, basically this thing would get crossed out. It would be 15. And then if you notice, what you have is you have 75 plus 15 minus 90. That just equals 0 for F net and the X, which means that acceleration is equal to 0 in that case. So if friction were 15, you'd have an acceleration of 0. Okay. Next one I wanted to do is the gymnast one. Maybe. Okay, so this one, what force does a trampoline have to apply to accelerate a gymnast straight up at 7.5 meters per second? Basically what we have is we would have mg, and that would be 45 times 10, which is 450 newtons. So there we go. And we could call that FG if we want. But then we have the force from the trampoline. And the force from the trampoline is the only other force, but it's going to have to be a lot bigger. We don't know what that is, but that is what we're looking for. Okay. So don't jump the gun and just straight away apply Newton's second law and say, well, it's just F equals MA. Well, it's actually F net equals MA. Okay. And that is the key here, because F net is not the force you're looking for. You're looking for another force that is part of F net, but you're not looking for F net. So F net is actually equal to F sub T minus the force of gravity. So that would be F sub T minus 450. And now we can set this equal to MA. Okay. So that would be equal to 7.50 times 45. And then you get FT, when you solve for that, equals 450 plus and 7.5 times 45. I guess I'm going to have to calculate that. 33.75. Sorry, 337.5. And when you add those, that would give you 0.5787. Sorry, did that in the wrong term. So your force from the trampoline is 787 newtons up. So hopefully you see that you do need to, it's worth banging out this free body diagram, because you are being asked for the trampoline, not for F net. Okay, so you can't just apply Newton's second law blindly there. Okay. All right. So the next one I wanted to look at is the one with the baby being weighed. Grab this as well, grab the diagram as well. Now, there's a number of different ways, or there's a couple of different approaches you can take this. What is the mass of a child in the basket if the scale reading of 55 newtons is observed? Well, this is fairly straightforward, but what we could do, what I would do for part A, is I would just do a free body diagram of the baby. And the free body diagram of the baby basically has F sub G and then tension 1. And tension 1 is basically the scale reading. It's worth knowing that. Okay. So tension 1 is basically what the scale is going to read from there. And these two are equal again because A is equal to 0, A sub Y is equal to 0. So the tension 1 is equal to 55 newtons. Okay, which means if those are equal, because acceleration is equal to 0, then force of gravity is also 55 newtons. That is equal to m mass of the baby times g. I let g equal 10. You have 55 equals mass of the baby times 10, and you get 5.5 kilograms equals mass of the baby. So do remember that SI is in kilograms, okay? So now what is the tension in chord T1? Basically, we've already done that. That's both A and B. The idea is that the scale, like I think the way you're supposed to solve this is to think that the scale is reading the weight of the baby. In fact, what the scale is technically reading is the tension. And the way you know this is that you could basically change the scale reading by pulling on it by increasing the tension. So that's how you know it's measuring the tension, in fact, instead of the weight. You set it up such that in this situation, such that the weight is equal to the tension, and you're good to go from there. All right. Now, tension 2. So now they're looking at these two up here. Now, there's a couple of things. One, they note that tension 1 is experienced in two places, but they are equal and opposite. So there are a couple different ways to do this. If you want to find tension 2, one way of doing it is doing the scale plus the baby as a system. So you're basically going to combine these into one object. Your mass of your system will be mass of the scale plus mass of the baby, which would be 0.500 plus 5.5 kilograms, be 6 kilograms. And then we can just take a look at the free body diagram. In this case, it's just force of gravity, which is going to this time be mass of the system times g. And then that is counterbalanced by T2. So, whoops, T2. So these two are then equal to each other as well. So you just have T2 is equal to mass of the system times g. So T2 is just 6 times 10. T2 is 60 newtons. Now, alternatively, you can just look at the scale. Okay. Now, if you just look at the scale, then your M is equal to 0.5 kilograms. It just 3 sig figs, but that's fine. And what you get is you drop this and you get, okay, FG is equal to 0.5 times 10 is equal to 5 newtons. But also going down on the scale is tension 1. And that we found back in the first part was equal to 55 newtons. So take a look. Tension 1 right here is pulling downward on that scale. So that's why you have 55 newtons right there. And then the only thing up on the scale, whoops. Oh boy. Okay, that's interesting. The only thing up on the scale is T2. All right. So setting up, again, we still know that acceleration is 0. So setting up a F net, T2 is up, and then T1 is down, and force of gravity is down, and those should be equal to 0, again, because acceleration is 0. So we solve this, and we get T2 equals T1 plus Fg. That's just going to be 5 plus 55, which will be 60 newtons, which for T2 is exactly the same thing we got up above. So there are two different ways of approaching that problem. Both of them work just fine. All right. Okay, last one I want to take a look at. So, whoops. Okay, there we go. So we have here, a nurse pushes a cart by exerting a force on the handle at a downward angle of 35 degrees below the horizontal. All right, the loaded cart has a mass of 28.0 kilograms. So I would just write that 28.0 kilograms. Ooh, friction is equal to 60 newtons. And then the applied force, we don't know what that is, but it's at 35 degree below horizontal. So first thing we want to do, draw a free body diagram. All right. So we are definitely going to have a force of gravity. We should probably get the system of interest. It's going to be the cart. We don't know enough to include the nurse in the system. Like if we had the nurse's mass and we had like the force of friction on the nurse and things like that, maybe then we could include the nurse in the system, but we just don't have enough information. But we can do the cart. So the force of gravity would be 28.0 times G, which would be 280 newtons. So I'll write that over here. Actually, I'm going to write it below. F sub G equals, and I'll just do 280 newtons. You guys know how I found it. Consequently, we are going to have a normal. Now, some people will reflexively put normal down, and this is on flat ground, so this is the right direction. Some people will reflexively make the normal equal to gravity, and that is actually a mistake, okay? And we'll see why in just a minute. But the first thing I would do, I'm going to make a dotted line to note the horizontal, because I need my F applied, because oh, geez. Okay. F applied because the angle is 35 degrees below the horizontal, like so. Now, the last force we have is going to oppose the acceleration. Right now, this thing would be accelerating to the right. So the friction and also the surface is horizontal. So friction is always parallel to the horizontal. That's another way to think about that. Okay, so friction is then equal to 60 newtons right there. Okay. Now, this is where we have we have forces at some angles, so we're going to have to break this up into components now. Now, here's the thing. When we do this, we're going to need both X and Y components. So sometimes people they like jumping directly to the net force equation. Sometimes people like listing them first. Up to you. Like in the X, I would look at this and I would say, okay, it would be minus the friction. So that would be because friction is going negative. All right. And then I would also say, okay, it's FA, but just the X component, because A is going partly in the X and partly in the Y. Now, to do that, we can break FA up into its X component, and that's just the way this is drawn. FA cosine 35 degrees. Okay, so that's fine. And those happen to be the only two forces. All right, so the key here is we actually have enough information to answer this now, but I'm gonna finish up. The normal force, we don't know what this is, but that is positive. We would have negative force of gravity, so I'll put negative 60 there. And that would be negative 280. And again, I'm making it negative because the free body diagram indicates that it's down. And I also have negative FA sub y, which would be negative FA sine 35 degrees. Okay, so we don't know what FA is, but we do know that normal is going to have to cancel out because, again, A sub y is equal to 0. And that's just true because this thing can't accelerate up or down. That's just by virtue of the fact that it's on flat ground and it's not leaving the ground. We know that normal will then have to be, so it would be normal minus 280 minus FA sine 35 would have to be equal to 0. So your normal is more than gravity. It's 280 plus your applied force times sine of 35 degrees. Okay, so that's why normal has to be greater than. Now we don't know what FA is. We're going to use, we're not actually going to find normal, but I just wanted you to see that. But we're going to use, we can find FA by knowing the x acceleration. So it says what force to move at a constant velocity. The key takeaway from this is that your horizontal acceleration is 0. Remember, constant velocity means an acceleration of 0. So we have A sub x is equal to 0, which means F net in the x direction has to be equal to 0, which means that FA cosine of 35, taking the positive, subtracting the 60, which was the friction, should equal to 0. That is going to give us FA equals 60 over cosine 35 degrees. Okay? And solving for that, that's going to give me FA equals 73.24 degree or newtons, not degrees, newtons. Okay. So that is how you could find FA. From there, you can go back and find the normal from FA. We don't have to in this case, but you could do that. Okay. Now, the last one I wanted to look at was the one that I came up with where it's just sitting on the where the I thought this was going to be the last one, but I do want to look at this one where you have the mass sitting on the inclined plane. So this guy right here. Box sits on an inclined plane at an angle of 30 degrees. So we set up that basically what you had here is you had something like this, 30 degrees, and then like so. Now I'm going to do something a little wild. I'm just going to draw the free body diagram directly over my picture. So we would have FG, and that's equal to 10 kilograms times G, which is 100 newtons. So that's fine. Our normal, we said, was perpendicular to the surface. So that's fine. Now, for that reason, we definitely can't say normal is equal to gravity. One, it's in a different direction. And two, it's not necessarily going to be equal. Then we had a friction force in that direction. Now, how we're going to look at this one, basically what we're going to do, we're going to make a new coordinate system where my x-axis is going to be in the plane of the inclined plane. So my x-axis is right there, and then my y-axis is right there. So we're tilting our coordinate planes. Why are we doing this? Well, among other things, it makes sorting our x and y forces a little easier. Okay, because in that case, normal is the only force that's in the upward y direction, and friction is the only force that's in the positive x direction. Okay, now gravity is doing a little bit of both. Normally we think of gravity as just being vertical, and it is, and normally we make that y, but gravity is not just in the y in this case. Okay, so oh geez. Okay. Sometimes these things just crash, and I don't know why. But in any event. All right. So, oh shoot, I gotta share the screen again. heck? There we go. Okay. Now when it comes to gravity, basically we need to break gravity up. So we're going to have a component that is in the y direction that we've drawn. So that will be FGY, and that'll be negative. So negative FGY. And then we'll also have a component that is in the x direction, FGX, and that will be negative. Now we know this thing is stationary, so we know that a sub x is equal to 0 and a sub y is equal to 0. Now what this implies is that the friction is equal to the x component of gravity in this system we've drawn, and the normal is equal to the y component of gravity in this system that we've drawn. Now, how do we find what those are? Well, you need to do a little bit of geometry here, but we know this angle labeled is 30. We also know that gravity makes a perpendicular with the horizontal, which means that according to the rules of triangle, that angle right there has to be 60 degrees. Okay? Now, the other thing we know is that this angle right here, that is 90 degrees. So that's the angle between the x-axis and FGY. Now, if that angle is 90 degrees and the angle between gravity and the x-axis is 60, that means that this angle right there has to be 30 degrees. Okay, so that's some triangle geometry. Just angles in a triangle have to add up to 180, and then doing just complementary angles there. So that angle is 30 degrees. And it turns out that this angle and this angle are always equal for these setups. Okay. Now, it's going to be a little odd because this time FGY, it's actually adjacent to that angle. So FGY is not going to be the sine theta. It's actually going to be cosine theta this time. So sometimes people will get in the habit of just writing the y component as sine theta, and that will throw you off here. You got to look at the geometry and really see what's going on. Now, negative FG, so that would be a negative, and then this one will be negative FG sine theta, because the other one was cosine. So the friction force is then equal to FG was 100, so that would be 100 sine 30. Normal is equal to 100 cosine 30. And this ends up being 50 newtons. And I think that one ends up being like 83 newtons, as I recall. Just got to do. I think that's what it rounds to. It's square root of 3 over 2, so 86.6 newtons. So 86.6 newtons. This would be 50.0 newtons. Okay, so that is how we would find those. Now, we only were asked to find the friction, so friction is 50.0 newtons, but that is basically how you would do it. Okay, so the lectures have gone a bit long. Some of these examples, hopefully you found them useful, but I'm gonna go ahead and end that there and get this thing posted. So I'll see you guys in the next lecture.